Hello. So today we're going to be adding on to what we did last time with vector spaces by introducing a new thing called the inner product. Okay, so far we've got the vector space V with the vector space addition, the vector addition, and scalar multiplication. Now we're going to add a new operation called an inner product. Okay, so the vector space with the inner product now becomes an inner product space. Okay, so an inner product space is a vector space. Okay, so that's the starting point. We're given a vector space V over a field. Okay, and like I said last time, we're going to be dealing with complex vector spaces. So the underlying field will then be the set of complex numbers. Okay, so this vector space with an inner product given by a map. Okay, so this inner product is just a map. It's a map with a funny name, but it looks like this. Okay, so usually when we provide maps, it's given like F and G and so on. But like we saw last time, the vector addition is a map, okay, but it just has the name plus. And the scalar multiplication is also a map, but we use dots. Okay, so just because we call something a map or a function doesn't mean it has to be something like f and g and h of x and so on. Okay, so this is a map. Okay, so it's a map from v cross v into the underlying field. In our case, it's going to be C. Okay, so what does this do? It takes two vectors, so let's say u and v, and it produces a complex number from it. And much like with the vector addition map and the scalar multiplication map, we write it differently. So instead of having f of uv, for example, this map name f, in this case, we write it with this bracket notation here. Similar to how the vector addition map plus, we wrote in between the vectors. Okay, so it's just a bit of different notation. Okay, so let's look at some of the properties of this map or this inner product. So properties. Okay, number one, if we have the inner product with the zero vector, then this is the same thing as this, so we can swap them around, and this must give zero. Okay, so that's just one of the properties that this inner product must have. Okay, number two, the inner product of a vector with itself is zero if and only if the vector is the zero vector. Okay, so if you have two different vectors, then they can't have an inner product of zero with it. So if the two vectors are the same, okay, they can't have an inner product of zero. If they're different, they can. Okay, but if the inner product with itself is zero, then it must initially be the zero vector. Okay, but it is possible to have VW being zero if they're different. Okay, number three. Okay, if we have the inner product of V with some linear combination, let's say alpha U plus beta W, then this is going to be equal to alpha V with U plus beta V with W. Okay, so we see that we have what's called linearity. So we're going to speak more about that later on in the second slot here. Okay, so the alpha we can take out of the inner product, the beta we can take out, and then we can separate it over the plus. Okay, we call that linearity. Now, this is the physics way of doing things, okay, where we have this linearity in the second slot. So let's just make a note here. This is the physics way. Okay, if you are looking on Wikipedia, for example, or other online videos or in math notes, you may see that there's linearity in the first slot, not the second. So linearity in the first slot, that is commonly used with maths notations. In physics, we have this linearity in the second slot. Okay, so please just keep that in mind if you're looking at online solutions that may be from a maths textbook, that is the other way around. Okay, but since this is a physics course, we're going to be sticking with the physics way of doing things. Okay, so please just keep that in mind. Okay, number 4, if we have V with W, and then we swap the order, so we put V in the second slot, W in the first slot, then this is the same as complex conjugation. So we can swap them, but then we get the complex conjugation of the result. Because remember, this inner product gives us a complex number. So we swap them, we pick up that complex conjugation there. Okay, and then with this in mind, this complex conjugation, if we swap the arguments, if we use number 3 and number 4, this gives us the linearity in the, there's the linearity in the second slot. If we swap it around, the alpha and the beta are going to get complex conjugated. And so if we swap this around, so we get alpha u plus beta w with v. Here we get this complex conjugation. So we get alpha x conjugate u with v plus beta conjugate w with v. Okay, and again, this would be swapped around if this was the maths way of doing it. So 3 and 4, we would have the opposite behavior in math textbooks. Okay, so this one and this one, please just keep in mind which way we do things. Okay, so those are the basic properties of the inner product. So I will post some extra homework problems just to go through these, just to get a proper understanding of the inner product and how we work with it. Okay, so once we have an inner product, we can use it to define more things. So we can define a norm or length of a vector using the inner product. Okay, so of course you can define a norm separately from an inner product. Okay, so that's perfectly fine. So you can have an inner product defined one way, you can have a norm defined another way. However, since we have this inner product, we might as well use it to then define the norm. And that will give us a way of measuring the length of a vector. Because so far, these vectors have just been objects in the vector space. We can add them, we can scale and multiply them, but they haven't had any length yet. Okay, they've just been those vector objects. Okay, so how do we give it a length? Well, we say that the norm of the vector v squared is given by the absolute value of the inner product with itself squared. Okay, so that is the length of the vector. And we will see this appear later on when we look at Hilbert spaces and quantum mechanics. Okay, so this over here will play a big role in finding the probabilities of certain events happening. Okay, we will use this, the inner product to define this norm, and then we will use the norm to define certain probabilities. Okay, so once we have this norm, then our vector space becomes what is called a normed vector space. Yeah, but we don't have to worry too much about that. So our vector space, or I should say inner product space, because it's got an inner product now. Inner product space, becomes a normed vector space. Yeah, because it's got a norm now. And later on, we will add a few more things, and then we will eventually get what is called a Hilbert space. Okay, so a Hilbert space comes when we add this idea of completeness. So we won't get into too much detail with that. I will just do a brief introduction to that. So we take our inner product space with the vector space, we add completeness, and then we get what is called a Hilbert space. And that's what we're going to be using when we do quantum mechanics. So in quantum mechanics, the states of the system are vectors in the Hilbert space. Okay, but we're going to be doing that later on. Okay, so that is a brief introduction to the idea of an inner product space. So just take a look at the homework problems for more details on that. Okay, but now we're going to be looking at a different way of writing things, so different notation for vector spaces and Hilbert spaces, and we call that Dirac notation. Okay, so Dirac notation. Okay, so this is the typical notation that is used in quantum mechanics, and it's just a different way of writing vectors and inner products. Yeah, it's slightly different notation. It's a bit useful when dealing with calculations. Yeah, so how does Dirac notation work? Well, the Dirac notation comes from the use of the inner product in quantum mechanics, so we use it quite a bit. So if we have the inner product U with V, like this, we make a slight modification, and instead of the comma between the two elements, we replace the comma with a vertical line. So the inner product between two elements like this becomes U vertical line V. Okay, so we drop the bar to represent a vector, and the comma becomes a vertical line. So we drop the bar above the vectors. And we replace the comma in the inner product with a vertical line. Okay, so that's how we represent inner products in Dirac notation. Now it goes a bit further than this. Instead of writing U and V as single vector elements like we had before, we now incorporate this inner product notation with the vector notation. So this inner product here with U and V, we separately write these elements as, so we write these elements as, okay, so UV as an inner product, we literally split it open, and we have U as the one element and V as the other element. So we see that this inner product notation has been blended in with the vector notation. Now, this element on the right-hand side, we call that a ket. Okay, so those are the kets. And the element on the left-hand side we call a bra. And together they form bracket or bracket. Okay, I should write bra. So it's bra, ket, like together, like bracket. Okay, because of the brackets that we previously used for the inner product. Okay, so this way, the notation for inner product is thrown away, and instead we use this notation of having bras and kets, and together they form the inner product. Okay, so we just write them together, and that is an implied inner product. Okay, so we don't have a separate notation for the vectors and a separate and for the inner product. It's now together. Okay, but this is very different to what we had before, where u and v were both from the same vector space, and the inner product was simply an operation on the vector space. Now, these elements u and v are now from separate spaces. Okay, so what do I mean by that? Well, I mean v as a vector or as a ket is from the vector space, so that is as we had before. And this u is from a different vector space related to this one, but it is from the dual vector space. And that is from v star. Okay, and what is v star? V star is a vector space on its own related to v. It's the set of all functions, let's say f, which map vectors from v to the underlying field C. Okay. So together, this U and the V, instead of being an inner product on two vectors, we now take that same operation and interpret it as U, which was previously a vector. We now treat it as a function from the vectors to the complex numbers. So with this in mind, we could have written u, which is a function. It eats a vector v, and then this becomes a complex number. Okay, so it behaves the same way as an inner product. Okay, the u and the v, we inner product them, and then they become a complex number. But here, the u we treat as a function now, which eats the v and produces a complex number. But instead of writing the brackets as we would with a function like f, for example, instead we just write them next to each other, as we had with the inner product. Okay, so it's a slightly different way of seeing things, but it behaves exactly the same as the inner product we had before. Okay, it's just a slightly different way of interpreting what's going on. So instead of an operation that takes in two vectors, the first vector we take as a function, it eats the second vector and produces a complex number. Okay, but the nice thing is that this v star, the dual vector space, is in one-to-one correspondence with the original vector space, okay, for finite vector spaces. So before, when we had, let's say, u and v in a product, where u was a vector, since it's in one-to-one correspondence with this dual vector space v star, this is entirely equivalent in taking this u vector, replacing it with the u dual vector, u, and then having v. Okay, so these are the same behaviors. Okay, so it's a little bit odd, but it is not too bad. Once you wrap your head around this idea of the vector space and the dual vector space, it should make some sense. Okay, and all the properties that we went over before, those are exactly the same. Okay, so one more thing on this one-to-one correspondence between the vectors and the dual vectors. Since there is a one-to-one correspondence, there should be a way of getting from the vector space V to the dual vector space V star. And the way that we do that is with the dagger operation. Okay, so given V from the vector space V, so that's the original vector space, we get the dual vector, or the bra, V, which is an element of the dual vector space, using the dagger operation. Okay, so what does that mean? So this bra V is equal to our original V from the vector space, and then we use this dagger operation. Okay, so this dagger operation allows us to take vectors from the vector space and convert them into dual vectors from the dual vector space. Okay, and it goes both ways. So the dagger operation on a dual vector then takes you to the original vector space. So you can go back and forth since they are in all sense equivalent. Okay, so let's have a look at this dagger operation for a finite vector space. So let's say our vector space is C3, okay, with all of the usual addition and scalar multiplication. Okay, so if this is our vector space C3, we can represent the vectors as column vectors. Okay, so an element from here, let's say V, can be written as a column vector A, B, C, where A, B, and C are complex numbers. Then, if this is our vector space, we can construct the dual vector space V star. Okay, and then those elements would then be the bras V, so we can use the dagger to get from one to the other. And in the dual vector space, we define them as row vectors. So we have A, B, C. Okay, but it's a bit more than that. This dagger converts the column to a row, but it also does complex conjugation. Okay, so we can view this dagger as complex conjugation and then transpose. Okay, so this dagger does complex conjugation and transposition. Okay, so column vectors become row vectors, and then the ABC becomes ABC complex conjugation, complex conjugated. Okay, and there's another word for this. This is also called the Hermitian conjugate. Okay, but we will just call it dagger. Okay, so we've got the vector or the ket V. Okay, that's a column vector. We can then use this dagger operation to get the bra V. Okay, they're in one-to-one correspondence. This will then be a row vector with complex conjugated elements. Okay, so with this construction done, we can then look at what the inner product does. So if we take the bra V and then the ket V, we can literally write it as the column, as the row vector with the column vector, okay, being multiplied. So we have the A star, B star, C star. That is our bra. And then we have A, B, C as the ket. We do the usual matrix multiplication, and then this gives us A star A plus B star B plus C star C. Okay. And then this, of course, generally, if these are different elements, so if we had a bra V and a ket W, for example, that would in general be a complex number. But in this case, we get a real number from this. Okay, and this is indeed the norm squared of V. Okay, because we have V in a product with itself, that is the norm squared. Okay, but in general, it's a complex number. Okay, so that is if we take V with V as an inner product. If we swap the order, we get a different product, okay, called the outer product. Okay, so let's look at that. The outer product. Okay, so if we write it the original way, it looks like an inner product and it behaves exactly the same as an inner product. However, if we reverse it, we get something called the outer product. Okay, let's see what that does. So let's say V is equal to 1, 1, and W is equal to 1, 2. Now, currently, these are both kets. They're both column vectors. If we want to do the outer product, one of them must be a bra, the other one must be a ket. So let's take this W ket and convert it into a W bra. So this, we can use the dagger operation. We swap this around to make it a bra. And as we constructed before, the row vector becomes a column vector and the entries become complex conjugated. But since they're real, they just stay the same. So we have 1, 2. Now, before, when we did the inner product, it was a bra with a ket. If we want to do this new thing called an outer product, it's going to be a ket and then a bra. So it will be V and then W. Okay, so V is going to be 1, 1. W will be 1, 2. Now, if we do the usual matrix multiplication, this won't give us a complex number because the numbers, the row and column numbers don't match to give us a single number, but instead we're going to get a 2 by 2 matrix. Okay, so what do we get? Doing matrix multiplication, we're going to get 1, then 2, then 1, and then 2. Okay, so we get a matrix. Now, this makes a bit of sense because if we look at this construction here of the outer product, if we take this outer product and then multiply it onto a ket, let's see what we get. So let's say U as a ket is given by 1, 0, for example. Then let's take the outer product, combine it with this ket and see what happens. So we've got V, W, and then acting on the ket, U. But notice that this second part here, this is just a complex number. That's a complex number. And then on the left-hand side, this is a vector or a ket. So the result is a complex number multiplied by a ket or a vector, and we're just left with the vector. So that is using the Dirac notation just to interpret what's going on there. But if we use the vector form, the column vector form, the row vector form, what is this going to be? Well, it's going to be V as we had it. So that's the 1, 1. Then it's going to be W, which we had as 1, 2. And then U, which is 1, 0. But we know that this beginning part is the matrix 1, 2, 1, 2. So this is equal to 1, 2, 1, 2 multiplied by 1, 0. And we see this is going to be 1, 1, which is a vector again. So we see that this outer product acting on another ket or another vector gives us a vector. So in terms of this column vector, row vector, matrix representation of things, we see we get the same behavior. So the outer product produces this matrix, which can then act on a vector to produce another vector. So just a note, the inner product is an action between a bra and a kit and produces a complex number. Is an action between a bra that will be on the left-hand side and a kit on the right-hand side to produce a complex number. Okay, and the outer product is an action between a kit, so that's on the left-hand side, and bra to produce a matrix for finite dimensional vector fields. Okay, so they are quite different. So just by swapping the order of the bra and the kit, we get these two different operations. So bra and kit, that's the inner product, has the same properties as we had before. It does all of that. If we swap the order and we have a kit and a bra, then it produces an outer product, which we can see as a matrix if we use this column vector, row vector representation. Okay, so those are the two operations in this new Dirac notation. Okay, so I just want to do one more thing on the inner product with given a basis. Okay, so far we've just been dealing with the properties without specifying any basis. However, for the vector spaces that we're going to be dealing with, we're going to be using bases quite a lot, going between bases. So it's important to see how the inner product works given a particular basis. Okay, so inner product given a basis. Okay, so let's say we have a vector space V with a basis. So given a vector space V with a basis. So let's say the basis is provided by the vectors 1 up to n. Okay, so here I'm just using the numbers 1 through n to enumerate the basis vectors. So before, when we had a basis, we could write it as v1 up to vn, but we can give it any name, really. So here we're giving it the name 1 to n. So we shouldn't treat these as numbers, so just rather treat them as some kind of label. Okay, so just because it's labeled number 1 doesn't necessarily mean it's the first vector or anything like that. It's just a label. So this 1 up to n here, these are just labels. Okay, so don't think too much about the actual numbers that we are prescribing to them. They're just labels. Okay, so if this is a basis, then any vector in the vector space V can be written as a linear combination of these basis elements, okay, as we saw before. So let's say we had a vector V. From the vector space, we can write this as alpha 1, 1 plus all the way through to alpha n, n. Okay, so we may not need all the basis elements, but then those particular alpha values would just be 0 if we don't need it. Okay, but in general, this would be the basis expansion for V. And if we had another element, let's say W, another vector W, this would be beta 1, 1 up to beta n, n, like so. Okay, so let's take the inner product with v and w and see what we get. So to do that, we need v with w, but note that we had v like so as a vector. We want v as a bra. So we need to use the dagger operation to convert it from being a ket into a bra. So the dagger operation was complex conjugate transpose. So all of the basis vectors, they get turned into bras, and all of the coefficients need to be complex conjugated. So this ends up being v as a bra would be alpha 1 star 1 2 alpha n star n. Sorry, that 1 should be the other way around. Sorry. Okay, so this needs to be the other way around, 1. Okay, so we took all the basis vectors and flipped them around, so the kets turned into bras, and then we did the complex conjugation on the coefficients. Okay, so we can now take the inner product between the two. So v, we can just put that in brackets here. So it's alpha 1 star 1 plus dot 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 plus alpha n star n. And then the w we can write as beta 1 1 plus dot 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 plus beta n n. Now, if we multiply this out, there are going to be a lot of terms. We're going to have the 1 with the 1, the 1 with the 2, 1 with the 3, all the way up to n. And then we're going to have the 2 with the 1, 2 with the 2, all the way up to n, and so on until we get the n with the n. Okay, and that is a lot of terms. So to simplify this, what we do is we choose a particular basis called an orthonormal basis to avoid all this multiplication. To avoid all this multiplication, we choose a particular basis Okay, so remember the basis isn't unique. We can choose any type of basis. However, there are particular bases that help with calculations. So in this case, the so-called orthonormal basis really helps a lot with this inner product. So we choose a particular basis called an orthonormal basis. And O and B, orthonormal basis, where the inner product between pairs of elements in the basis is given by the following. So if we pick the ith one with the jth one, this is given by delta rj. Now, what is this delta rj? Well, it is 1 if I is equal to j. In other words, if we take the inner product of a basis element with itself, we get 1. That is this normal part, okay, because it's normalized to 1. And it is 0 if I is not equal to j. And that is this ortho part. So we say that the vectors are orthogonal to each other. And if you remember your inner product from last year, the inner product or dot product, as you called it last year, we could write as a, b cos theta. If theta is 90 degrees, then they are orthogonal to each other, and the dot product or the inner product was 0. Okay, same thing here. So if these two vectors are different, then they must be orthogonal to each other. If they're the same, we impose normality, and so the inner product is 1. Okay, so if this pairwise inner product here is defined like this, we say that it's an orthonormal basis. And if we go back to all of the multiplication we had before, the element 1, the complex number of bra 1 with ket 1, that's just going to be 1, because we have 1 with 1, that gives 1. If we have 1 with 2, that's going to be 0, because they're different. And going through all of these, the only terms that will survive are where the two elements are the same. So the 1 with the 1, that will survive. 2 with 2, that will survive. All the way up to n with n, that will survive. Okay, so provided we have an orthonormal basis, V with W is going to be equal to alpha 1 star beta 1. And then the 1 with the 1, that's just going to be 1, so we can leave it out. Then we're going to have alpha 2 star beta 2, again, because the 2 and the 2, that gives us 1, so we can leave that out. Plus, and then the same thing happens for all the terms up to alpha n star beta n. And again, this is a complex number. So you see that choosing a orthonormal basis makes the calculation of the inner product quite easy to do. Okay, if we didn't have an orthonormal basis, then we would have a lot of extra terms to deal with. Okay, but for more on that, please look at the homework problems on inner product spaces. Okay, so that is everything for today. In the next lecture, we're going to be looking at eigenvalues and eigenvectors. Okay, so please go through your work on matrices that you did last year. So there's a few things under matrices that we expect you to know before we get into eigenvalues and eigenvectors. Okay, but if you have any questions on this material or the tutorials or the homework problems, anything like that, please just send me an email or you can visit me in my office. Okay, so all the details are on the course page. Okay, and then one more announcement. This Wednesday, we have tutorial 2 in the physics lab. Okay, so it's an in-person tutorial. Okay, so I'll see you then.